AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Welcome to today's AI for Manufacturing webinar. My name is Li-Hui Wang, a professor at KTH, Royal Institute of Technology in Stockholm, Sweden. I'm honored to be the moderator of today's webinar. The topic of today's keynote is entitled Artificial Intelligence and Industry 4.0, the Production of Tomorrow. We are fortunate to have Professor Gisela Lanza with us today. Professor Lanza is a member of the management board at the Institute of Production Science, WBK, of the Karlsruhe Institute of Technology, KIT. She has the Production Systems Division, dealing with the topics of global production strategies, production system planning, and quality assurance in research and industrial practice. In 2009, she received the Heinz Mayer Leibniz Award of the German Research Foundation, DFG, in recognition of the outstanding scientific achievement after the doctorate. And she was awarded in 2016 with the Federal Cross of Merit on Ribbon. She is an active member of the German Academy of Engineering Science, Architect, and the national platform Industrie 4.0, as well as the steering committee of the Alliance Industrie 4.0 Baden-Württemberg. In addition, a special focus of her research is placed on data-driven planning and control of production networks in order to translate corporate strategy into tactical and operative network design. In order to master the high-risk process quality, especially in immature production processes, Professor Lanza is also intensively engaged in the integration of inline measurement technology in production systems, as well as the intelligent method for the analysis of measurement data. The close integration with numerous companies, primarily from the automotive, mechanical, and plant engineering, secures the practical applicability and the industrial added value of their research work. Ladies and gentlemen, without further ado, please join me in welcoming Professor Gisela Lanza to the virtual platform. Please.
Great. Thank you for having me to this community about artificial intelligence and Industry 4.0. And I would like to give insight how we can use AI for our industry and how we can enhance
Professor
our
Lanza,
industry.
sorry
Yes.
to interrupt. There just seems to be a little bit of an issue with the audio still.
Okay. So it's not good enough. Yes.
It's still jumping a little bit.
Now better. If I continue talking, it's
Well,
still jumping.
Very clear now. Thank you.
Wonderful. So thanks again, and I will start, and Julian will interrupt me whenever the audio or something else doesn't work. So thanks a lot for having me, and I would like now to start with AI, how it's a huge tool for us within production. And this term Industry 4.0, you know, it's really famous here in Germany. And I would like to go to the next slide. Yes. As we have seen in the intro, we have to deal with that sustainable development goals. And I would like to focus with the goal 9, the industry, innovation and infrastructure. We in dealing with industry, with production in industry, we have to build resilient infrastructure, promote inclusive and sustainable industrialization, to upgrade our industry and to foster innovation. And here, when we look into these revolutions, when we talk about Industry 4.0, we have the opinion that we are now in the 4th revolution. We don't know if it's a revolution or evolution, but we are in this decade where we use digitalization, digital tools, and more with the availability of data, we can use artificial intelligence. Our algorithms, our procedure, they can help us really to gain this huge goal, the goal decoupling prosperity and resource consumption. That's our huge goal, and especially in production, that seems not, it seems to be far away. So we have to deal a lot with that. When we look, and only a short introduction in AI, I want to talk only about machine learning. And if we look here at the, let's say, Google search of keywords in the sense of AI, we see that the main part is about machine learning, about deep learning, but we also see it's getting stable. So we don't want to go back to a winter, AI winter, but we are middle of using it, improving it, and the big hype is here again since a few years. So let me just give that insight, our view of AI, and probably yours as well. We are, I don't know if we are at the goldfish or the mouse level, we are accelerating really fast, but still for me, AI, and for us, AI is a tool for us, which can assist us in every life position, in every, let's say, area, but especially in the area of production, I would like to talk about that. So I'm not talking about super intelligence or about strong AI. I talk about the AI tools which we can use today and tomorrow to improve and to maybe decouple resource consumption. Why is it like it is at the moment. So everybody's talking about artificial intelligence. I think there are some reasons and they could be explained, but I really like Andrew Nick, who said it's almost the same with electricity. And when we look back in the history, and probably our kids will then, or our grandchild can say if Industry 4.0 was a revolution or only evolution, but what it will be, it's like electricity, and electricity, it takes a while until it went into every area of our life. And meanwhile, can we live without electricity? I don't know, but we don't want to live without electricity. And as we deal here also with heavy machine industry, for example, still we are in the phase of having more and more electricity enabler also in the car industry. So, you know, I came from the south of Germany. Here we are in the auto land, so still we are in a kind of transition. So, but the main reason why we talk nowadays about AI and why we see these successes is on the one hand, really the computer power and the open access algorithm, and therefore really successful examples of use. And the last few months, we all get crazy about this ChatGPT. So for me, as I said, it's still a tool, and we have to get used to that, or we have to learn how to use that tool in a really powerful manner. And yes, when I talk about machine learn, I have to I want to refer to the standard taxonomy. And there are these popular examples. Let's start here with let's say with the supervised learning, and we have here algorithm, and I want to show now in the following always this translation from this algorithm, probably from another area, translate it or transfer it to production. And especially supervised learning is used a lot for quality assurance, for detecting failures, and here are detecting patterns and say, okay, this is the right variant. So here variant detection, but you can also use it for, let's say, standardized failures. In the unsupervised area, the difference is the not labeled data, and that's also really nice to not having all this preparing time to labeling the data, but for quality at the moment we are a little bit too or scared to use that maybe, but when we go into this unsupervised, we see a lot of nice algorithms for clustering, for classification, and here I would like to show an example for showing product similarities to automate product development. It sounds heavy, automate a design process. I only speak about a detailed design, really, and let's say a repetitive working, what we do as engineers, so we can really increase here efficiency, not only at the shop floor, but within our whole industry. And then the third class, where I think as production planner, we have a real powerful tool. It's the reinforcement learning class. I also will show an example for order dispatching, but as we have a lot of decision processes within our area of production planning and control, here we can use that methods to handle a complexity. So having more data on the one hand, and we have this data meanwhile more than in the past in industry, but still not big data. So here there are tools which we can use. And for that, I will try to use this taxonomy here. It's incomplete, clear, and we will see a lot of our approaches combine different methods. But I will try to give one example for each of these main classes, starting with the supervised learning, and here clear using neural networks. I think that would be the classical one, but I would like to show how we can use pre-trained neural networks and transfer them to our area of production. So I choose the first example of the remanufacturing because that's probably our next big thing. How can we overcome our linear production patterns towards circular production or circular economy? And for us production guys, how can we deal then in the factory with that old used products? And at the moment, that's more niche, somewhere done where you have low wages because it's done manually by worker, and that's subjective. And there are a lot of failures are done with that. But the people are trained, small amount, low volume production is that at the moment. And if we want to do it in a big scale, in an industrial scale, we have to automate it. And here we have research in developing a robot-based inspection. And this robot-based inspection has a lot of challenges because when we look at this used products called cores, they are totally different. So the circumstance, how they come back, the degradation is always individual. So, and we don't know where are the region of interest, where are the failures. It could be everywhere at the product. So corrosion, for example, that's a huge issue where I want to show a small approach we had at the moment. It's a huge field. Yeah? The whole process has to be automated or autonomous because the product differs. We have a lot of different variants coming back. And this corrosion is something, as a quality guy, normally I can measure, I can quantify something, but the corrosion is, how do I quantify corrosion? And the people are quite good in deciding, then having, let's say, a class of good and bad, and this corrosion is okay, we can deal with that part of corrosion, but if it's more, then we have to stop the process and putting the product to scrap. So we designed here in the group a multi-stage architecture using these neural networks, these pre-trained neural networks. As you have seen, we have the data acquisition with that robot, with a civet, we have the images. And with the first stage, we use a mask region CNN for segmenting the individual parts because motors or starters are starters. They are huge amount of variants, but we can segment the usual parts, this main housing or the gear, and we have some segments which we can identify and then have a class of similar, let's say, product components. We want to select the corrosion one. So in the second parts, we use here a lightweight mobile net to only have to distinguish between or the classification, is it corroded or is it not one or not one? And then in the last step, we want to go towards a quantification. As I mentioned, the people, they are well trained after a while. They know what it's okay and what's not okay. What can I put into the factory and rework? And here we tried to use the approach to quantify this corrosion to a, let's say, quantifiable value, which then I can address and put it through some, let's say, people judgment in the end, so I can quantify it. Going there more in detail, I would like to stress less the networks, more the problems we have using that kind of pre-trained neural networks. So here we use this mask RCNN with 50 layers. It's a pre-trained net on the ImageNet data set. And therefore, if we can transfer that to and we have really low data, we only had 146 images, but if we can use this mask and we manage to use that mask RCNN, we can use these deep neural networks and this, let's say, this power of this network and then fine tune it with our labeled data. And here we gain then not bad results, as you see here, only a few visual examples. We have this bounding box about the components. So in the end of this first step, we have the segmentation of our product with the components, because in the remanufacturing, the whole product will be disassembling to components if they are okay enough, and then reworked and built up to a new product. And maybe some of the components have to, I have to throw away because they are scrap. So with that information, with that single product components, now I go into the second step. And the second step is a kind of pre-selection step, because here I use a lightweight network only to do the pre-selection. Is the component one? Is it corroded or is it not corroded? So herefore I knew this, we use that mobile net. By 2, it's for mobile devices, so really a fast or easy lightweight network, which can do this binary classification quite good. But here again, our problem is that we our manual label data has a kind of unbalanced data, and here we use then the weighted cross entropy, weighting this, in that case, not worn data higher to come to a more balanced data set, so that the algorithm worked quite good. And in the end, we could reach org area under the curve about 86, so quite good results. With that middle step of pre-selection, we can go now in really the quantification of the corrosion. And here we use fine, let's say a pixel with a high pixel accuracy, a network which can quantify the pixels who are corroded and not corroded, but we don't have the data. So our issue is here that we implemented an automated pipeline with synthetic training data. And we took here random polygons and then take, let's say, 2 training data. One is a corrosion database and the other it's a clean part database. And then we masked this, let's say, these polygons, some corroded, some not corroded, and therefore we synthetically created training data, and that's our ground truth. With that ground truth, we could then use the unit ++ architecture, and this is really from the medical area a net which can do it on a really high granularity, and a high granularity which allowed me a pixel perfect or nearly pixel perfect segmentation. And here again, we had a really good intersection of union score, but as I mentioned, that are synthetical data, so we have to further improve that research and do a lot more in this area. And as I mentioned, this step with, let's say, quantifying corrosion is only one part of this visual inspection planning. We have other issues around this really complex manual process at the moment, what we want to automate, and this automation has to be done in an autonomous and adaptive way. So, for example, the view planning problem, post planning, what we're doing here with acquiring the data acquisition with the point cloud, we can do it on a clear YPP and a view planning problem, but here we wanted to also improve that and have less, let's say, less effort in making pictures. So we develop here autonomous next best view planning by using reinforcement learning. As I mentioned, that's really an algorithmic class of machine learning algorithms, which we try to use often because it helps us to make the next decision in that term. How can we optimize the number of robot poses? We want to minimize that by maximizing the data acquisition. So, and herefore we, at the moment, we do research with a soft actor critic algorithms, which can handle this continuous action space and can handle all this complexity coming from the product, coming from this, let's say, open space, or this space, what a robot with the flexibility we have in the robot system. So I think we can really automate here something what was unthinkable before. So far to this first example about remanufacturing, and I'm sure there are coming more and more examples, especially in that field. My second examples, I would like to stress more this autoencoder, and also really powerful to automate or to find out similarities. That's one issue. And here we have an example from another industry. It's a company who is who is producing, development, designing, producing a lot of sensors. Sensors for process industry, for chemical industry. It's Endres and Hauser, and we had a research project together, so we can talk about that. And they designing a lot of different sensors with a lot of different, let's say, clear features. But on the other hand, sometimes the people in the company are not sure, do they really need a customer individual sensor? Couldn't it be that there is already something, a housing or component or something within the database which fits also? Or could I use common features from other products? So here we have the situation that we have over the year a really large amount of CID models. And in that CID models, we realized that there is a lot of implicit knowledge, because the designer, they don't write it down what we are thinking, what he's doing, the next steps, and that he's clearly designing, let's say, geometries which fits to the production. And that was our issue as production. How can we bring our production knowledge better into the production, in the product design, and how can we improve even the product design by telling them what the production is able to do or not? I know a really old problem in our field, but maybe with the data we can do much more in the future. So in that step, we tried a first step to find patterns within these CID models. And then maybe we can learn from that patterns, find out what happens when somebody's starting to design. So I would like to go here step by step. So we have a lot of data, as I mentioned, it's CID data. CID data you have in different data formats. You have metadata or not metadata. So what we have done, we try to have only point clouds, because of these thousands of data, there was only one round through, or let's say each of this CID model had a point cloud, or we translated in point clouds. And with that point clouds, we then try to extract features with machine learning algorithm and find out similarities. And you saw that net between the focus of this approach is an autoencoder. We use that point clouds, use it in a standardized format, this 2048 in 3 dimensions, put it in our convolution layer, created this latent space with the global feature vector. And with that global feature vector, we can then, let's say, calculate in an easy way. But on the other hand, we then have to have the decoder where we can bring back this geometry again. And you see here all hyperparameters, how we deal with that, trained and tested, and it worked. So we could then see that this autoencoder worked. But here, maybe the next, here you see what we want to do with that global feature vector. One main issue is that we want to calculate this distance of this, let's say, geometry footprint of this product. So with that global vector feature, we can easily calculate the Euclidean distance between them. And with that distance, we can express the similarity of two different products. And here you see visualization in a TSNE, where you see different colors for different group of products. And these yellow ones looks not good because they are somewhere everywhere, but that are the housings. And when we look deeper in, we see that housings, they look not similar they look not similar at all. So the housing could look like other products, and therefore, yes, the algorithm, the autoencoder worked because that is so diverse within the housing. Others are better than here you see the flanges. The flanges here in the lower ground, it's really one cluster, and you could find it very good, where other flanges are similar to that housings. And again, with the, let's say, the visualization, what we see, we would say, okay, that works. This housing looks similar to the flange. It seems to work. Other good examples here, the covers or the O-rings, and here they are good classification. So with that working autoencoder, what can we do now? We wanted to use it to find out similar products. Maybe we don't have to design a new one, but also we want to give the designer assistance to tell him what his colleagues has done in the past, because we face the problem that also this company has new designers which are not experienced like the older ones who have done that maybe for decades. So we put all these input models, but not only the finalized, as I have shown in the database, but while he is doing the design, he get, let's say, a guess what could be the next design step. And here it's done iteratively, step by step. On the other hand, if we find out a similar product, we can then find out, can we produce it? Because if that design or if this geometry fits within a production area where we have experience already, where we know exactly the quality, where we know the costs even, then we can say, okay, this is a good design. You can finalize that because we are able to produce it. If you are outside of this, let's say, solution space of the production, then maybe you have to build or buy a new machine or something. Maybe you don't want to do that. So this evaluation of production-relevant product feature, that's so to say the main research focus of our work, but we do that all steps before because we think we can gain more knowledge out of this design. So going here more in detail, how looks that? I mean, that's assistant for the designer. And here you see again the workflow, the workflow coming from a CAD, translating these CAD models in a point cloud, this point cloud, then transferring or abstracted in this global feature vector. With that global feature vector, we can then calculate the geometric footprint of the components and find out with the Euclid distance or with distance calcul values the geometry similarity, and then translate it back to the CAD data and show the designers what could be similar as CAD models. And here you see results from that company. We have a new input model and do exactly that. In the upper part, it's done only with the clouds, with the point clouds. And in the lower part, it's done with metadata. The conventional or the CAD models out there, the companies, they do it normally with metadata like volume or bounding boxes. But here again, in this company, the problem was that this information was not 100% in all data. So we could only use a part of the data for this metadata. But again, in this example, not only that I have not all this metadata, the issue was really that we could have better, or we had better results based on that latent vectors only on the basis of these point clouds. Here you see the B and the A difference. Also interesting, this next step visits. So that he give really the next example with a lot of iteration. When we have a class with a lot of data within that component class, we could give the next step or give a hint what could be the next design step. And in the end, as I mentioned, the evaluation of production-relevant product feature, how works that? So this, when I find out which one I want to produce, when I have the final geometry and I have put it in a class of similar other products, then I can find out in which, let's say, solution space of the production area I am. And you see here the red input component. It's in middle of an area of production relevant product feature with, in that case, only the dimension of the part, which is done within one machine. For example, this machine tool here. And if the diameter is less than 60 millimeters and it's within that bound, then let's say the possibility is quite high that you can produce it. I mean, that's a simple example. You could say, okay, I can only read if it has the right diameters, then I can produce it. But it's more than only the diameter. That's more for visualization. It's depending on the geometry. So it's similar to these other red dots, and within that red dots are all similar products which are produced on this machine. So the possibility or it's very likely that I can produce it. If it's outside, maybe it's more difficult for me to judge in this early phase. So it helps me only, it's not a fixed data, but it helps me maybe to decide and say, okay, probably I have the right machine to produce this component or this product. So I can do it with with a logic and also put it within commercial software. So here, first step within that company with Creo, we show here how it could work if it would be implemented in a full scale in this CAD model in this program. So far to the designers, and maybe you will ask, okay, we don't need designers anymore? No, I really would like to stress that in designing and constructing a new product, there are a lot of routine work. And here we can only improve that processes. The design, the creative thing is not improved here at all. And maybe there are also research on that. Not only maybe there are, but here's in this industrial case, and we can really speed up the design process. And the people are happy to not doing all this, let's say, boring, maybe routine work. My next example is reinforcement learning. And here I would like to show a typical example of production control. Production control is, let's say, decision process. On the planning, we have more long-term. On the scheduling, more short-term planning. And we use here a semiconductor industry. Why? Because semiconductor has a lot of data since years. They have standardized machine interfaces, and you see here the need. It's increasing in the factories in the last years. We all know that story. So what we have two is that we have a really complex structure. It's a complex job shop. Here we have, especially in the front end, a lot of processes which goes iterative, depending on the result of the process 64. It then depends which one are the next process and how long it will take. So you see up to 800 process steps. It's Infineon in that case, also a collaborative research project, and it takes really a long time. And it's expensive product. So, and machines are really more, or even also really expensive asset. So we have to improve the utilization of the machines, also to come up with that volume increase. On the other hand, the throughput time is also important. So what I want to show is, again, only one task out of this whole production planning and control. It's the dispatching here in what to do with the next order, where to go to which machine, especially when there are more than one machine is able to do the next step. So yes, we have this production, and you can do it with automated vehicles, but in our case, there are people still in these clean rooms and bringing the one batch to the other machine. And so we simulate this whole process, and that's also one main advantage for us, that we can do this reinforcement algorithm training within the digital twin of our production. So we are used since decades to build up simulation tools in this discrete event simulation for this kind of problem. And then we choose and we develop the right model parts for the reinforcement learning algorithm. We can then easily assess it with that digital model, with that simulation, and then bring our results back to industry. But still, I have to say, it's a black box, or more or less black box. And here, when we deal about what to do in the next step, it's not, so the people, they want to understand, why do I do that? Yeah, we can prove that the reinforcement learning is even better than the rules, the heuristic rules they have, but still we are in the process how to make it more explainable. So going here more in detail, we have a procedure model to using this kind of reinforcement algorithm. As you have seen already, we started with the characterization of the use case, building up the simulation model, understanding the KPIs, the targets, and all that we need to really then model our reinforcement algorithm. And normally we do here alternatives and try to find out different architecture or different modeling techniques to find out and fine-tune that afterwards what fits best to our use case, to our problem. Therefore, we need to do the training, find out the correlation of the agents with the targets we set, and then also try to adapt it to different scenarios. Because what I didn't say at the moment is that we want to have reconfigurable production system, not only a fixed point, an optimal point, but we want to change our systems, and therefore we need to have algorithm. And here's a big advantage, that this machine learning algorithm can adapt very fast to new situation. That I have new volumes or other volumes than the week before. I have a new machines, or I have a really hard breakdown of a machine, and then can this algorithm or this scheduling algorithm then react to that? So this transferability and adaptability is a huge advantage, what we think can bring this machine learning algorithm. And as I mentioned, we are in the middle of this plausibility check to explain to people how it works, or to look more in this black box. But I have to say we are maybe only in the beginning here. So showing here these cases, the first case here with the layout. We have here 8 machines and 1 transport. It's a man in that case. 3 sources, 3 things. So the machines has different sources, as you've seen in the lower part. So the complexity, as I mentioned before, is on the one hand really this complex material flow and also reflows, as we have seen before. Typical for production is the stochastic Euler behavior of our machine, and we have a high variety of process times and product-specific machining processing. We validate 2 scenarios. In the one hand, more the transport shortage. So the one man here walking from one to the other machine, it seems to be more the bottleneck. On the other scenario, it's more the machine sort. It's what happens if the machines are break, you have a longer breakdown time, and we have large buffers and much more transport. In that case, not more people, but faster transport speed. So we simulate this complex shop with machine sources, orders, and modeling like Markov decision process. You see here all this normalization. And this is, so to say, our learning environment for the reinforcement learning. And with that now, we go now in the modeling of this agent control. Here with first of all, we have to choose the right optimization or the right reinforcement algorithms. And we select here this trust region policy optimization. Why? Because it's already famous for scheduling and it's robust. It's converging very fast. On the other hand, we know it's really sensible according to that model reward or the reward modeling. So we now, after you choosing that, and we can also choose alternative algorithms, we have now to go in the model, the action representation, the state and the reward. And I would like to focus the state and the reward. As I mentioned, even especially the reward is really crucial. How much information do we put in this reward? Then it helps to have a converging fast, let's say, fast training period. On the other hand, how good is it then in transferring to other scenarios? So starting with that state representation, we select the relevant data. Here you see this example with the remaining process time, with the stock, the location, where's the person, and all this with data processing is done by one-hot encoding. And clear, we need to have this data. And as I mentioned, in that kind of industry, we can easily have past data from the past and, let's say, abstract them for our model so that we could then have the real quantitative data. And what's now important is that we need this domain expertise and have then the relevant decision, relevant data. When it's coming, if it's coming to the reward representation, I have to define my target values. And here we have different architectures, but we choose then the main two is on the one hand, machine utilization. As I mentioned, this asset, these machines are really expensive and should run 24 hours, 7 days a week. So this utilization, and the average of this utilization is one target value, and the other is the order throughput time. And the order throughput time, we didn't change now the processing time. So we focus on the waiting time in buffers, in inbound, outbound buffers. That's the main focus. We see a difference by choosing another dispatching algorithms. So we have here different parts of the reward function, the capacity utilization and the execution time, focusing on this waiting time. And we also have a constant and action waiting to, let's say, stabilize our algorithms. So with that, we now can go into, in this training, and you see here the needed iteration. Yes, it's when the performance is then comparable to the rule-based. Maybe I forgot to say, in this kind of complex production systems, we can't have an optimized target value or the optimization. We have heuristics, which is rule-based, like first in, first out. So if a product is transferred to a buffer, then this one is first in, that will go first out. And such rules help then to do the scheduling and dispatching in kind of production. So it's a heuristic. And you see here the comparison to one heuristic to the FIVO. Yes, we have this, let's say, this first learning phase until it's stabilized, and then we can have compared results to this rule-based benchmark. So we can then state, okay, it can work with that system. And what is really interesting, how does it work when we change the system? As I said before, we now calculate two different scenarios. Let's say week 1, where the transport is more the bottleneck, and then week 2, where more the machine is the bottleneck. And how can this, let's say, this agent behave then with that change? And what we see, yes, in the beginning, we have this long learning process, but it's transferring quite nicely or adapted to the new situation. So what that means is that we don't have to go in and set up new rules when the system is changing. The agent can really adapt to new circumstances because this environmental, this change, and then the agent can adapt. And that's a really big advantage compared to what we have at the moment in this industry. So therefore, as I mentioned, still a problem. Do we understand what it's doing? Can we explain the behavior of this reinforcement agent? And here is one try to have a plausibility check where you see the best reinforcement agent shown in the table, utilization to waiting time. And you see the Pareto front, always there are also worse reinforcement agents, but we can get even better or the same results than here different kind of rule-based, not only the FIVO heuristic you see here, also nearest job first or empty machine algorithms, and it works. I can explain a part that it behaves similar in that point, it behaves similar to rules, but it's only
Gisela, it looks like we've lost your audio.
Oh, are I back?
You're back. Thank you.
Should I go back to the slide? Maybe I continue.
Yeah, just continue. Exactly. That's fine.
Yeah, I come to an end. I want to show you that there is high potential. I only showed 3 examples, but there is a huge potential what's coming up. Here, we have some issues. We have always too less data, small amount of data. We have then to transfer, let's say, the knowledge from other areas maybe. Then we have the issue of transferring and having not the true ground of data. But as we spoke about Industry 4.0, with all the sensors which are coming in, where we can really have more data, then therefore I think that's the big challenge we still have, but we will have a high potential, what you see here. So maybe let's stop with that one issue that I think for us in production, the goal 12 will be the next thing, or the thing which we really have to deal with, that how can we, let's say, overcome these linear patterns, as I said before, and decouple the research consumption, and on the other hand, our prosperity, our industry value, which we get with the production or industry area. So some ideas we have, yes, we have the vision of a perpetual product, bring in old products, then rework them, bring them in, bring new features in, and yeah, bring it back to a second, to a third, to an endless life. So I think we have today a lot of tools which can help. Maybe this human-robot collaborators is one of the strongest one, where we really can have this adaptive systems, but also the planning. So for that, thank you very much. And I'm more than happy to answer your question. And I'm more than sorry that with the acoustic, there were a problem. Hopefully, you understand a bit of that, what I try to explain, and I'm really happy to be with you, and thanks a lot.
Thank you very much, Professor Lanza. This is a really interesting and comprehensive keynote presentation today. You also addressed through different examples how this AI-based approach can contribute to improve sustainability in production environment. You first talk about robotized corrosion detection, quantification, then go through another example, how to capture the implicit knowledge from right from the already designed CAD models. That's also very interesting. The third topic you covered is complex job shop production control, especially in semiconductor industry. Now I would like to invite online audience to raise your question. You can use the chat box. Here, I already have one question came in, and Professor Lanza can also see the chat box. Very interesting indeed, Professor Lanza. Maybe I didn't get it. Is your perspective on AI more of a technology, a tool view, or more of a Bostrom vision? So this question is the first arrived from Norbert.
So what I've shown is more on a toolbox, using it as a toolbox within our existing industry. But I would say it's only the beginning. So they are coming more and has to come more. But at the moment, what I have shown, I would say it's really on a technological level. It's right. But I have to say, as I mentioned in the last example, if the people don't, let's say, trust the system, they don't use it, especially in planning. And as we deal a lot with planning and decision processes, I can't stop only with the technologies. So this explainability, interpretability, understandability, it's getting more and more important. And here we need help.
Mm-hmm. Thank you. Well, we are waiting. Perhaps I can also ask a couple of questions. I think this robotized corrosion detection quantification is quite an interesting topic. You use a vision-based approach. Of course, the challenge is how to know the internal corrosion because it's not visible. And for example, inside of a gearbox or some other containers, when they are put in a harsh environment, how to detect corrosion inside non-visible is a challenge, perhaps not possible to use a vision-based approach. Do you have any thoughts that can be useful for us to look into the future?
We are doing in research, we are now starting the research on computer tomography. because these computer tomographs, they are really huge. You can put in your whole core and then see what happened, what you can see. But we are still in the beginning. We are not sure, can we see everything? And the second part, it's still it's really expensive. So I'm not sure if we can use it for everything. So the typical process in industry is at the moment that's not only an initial inspection or quality control, it's iterative. So you start in the beginning with the initial, what I have shown, and then you start to disassembly and do it again. And that's doing the worker widely is disassembly. So we have to have this perception during the whole disassembly process and coming step by step more in the inner part of but still it's outside. Yeah. And so we need to have also functional testings and some tomography solution how to look into the product inside. So, but you are totally right. We have a whole bunch of sensors and a whole bunch of tasks what we have to do. It's a research project or a program where we want to go in for the next 12 years. I really think that we have to do a lot of things to solve because we are only in the beginning at the moment.
Yeah, regarding the second research example topic, you mentioned the knowledge, implicit knowledge discovery or capturing from a CAD model. I guess the first assumption must be that the CAD models are well designed by professionals, because the CAD model also can be designed by a junior or immature design. That is out of a question. Then there's an implicit knowledge from experienced designers and engineers. Without talking to them, sometimes they are not approachable, not accessible. You can readily retrieve them from the CAD model. So this is very interesting to me as well. If, for example, those designers or engineers are accessible colleagues around, how to capture their knowledge directly? Do you consider any research in this implicit knowledge capturing from human designer and engineers?
I know colleagues who are doing that. So, for example, the perception of looking where the designer is looking on. So you know how it works, the step by step. But we didn't do it. As I may try to mention, we try to fix that production co-design. So we wanted to automate, let's say, the production issue or put the production related information into the product design, but we wanted to do that, and then we started to do all that similarity issues, and we were surprised, and also the colleagues were surprised how much information is already in that point cloud. So that was the surprising, because as you mentioned, normally you would say, okay, this knowledge, how he's doing that, it's in the brain, you have to ask him and you have to know what step by step is done. But that was on the one hand, that if you see only the result, and we also see which kind of these products are successful or not. I mean, if you have a database with 3,000 flanges, let's say, and the flanges which you sell 40%, so you should say, okay, something is successful with that flange. Maybe it's only the marketing, it's clear, but sometimes it's correlating, and we know the costs then and the production. So that was the aim. But what you mentioned is going much beyond that, what we are doing. So really understand what the designer is thinking by constructing, by doing the CAD model. And I know colleagues from the product development, they try really to understand that by learning and eye tracking and stuff like that. But at the moment, we not.
Now we have 3 new questions came in. The first one, thank you, Professor Lanza. How do you think the large generative AI model like ChatGPT will alter or can be will affect and can be applied in the manufacturing domain?
Yeah, that's really interesting because everybody, I mean, it's fascinated by using this Chat GPT, and we are still thinking of how can we use it. I don't have really good ideas, I have to say, because I think that the knowledge, the domain knowledge, is too less within the. I have to train this neural network because with real data, I ask specific question, and it was really hard to find it out. Whenever you ask this chat about artificial intelligence, you get perfect answers. But if you ask them about what's the difference between drilling and milling, then you get somehow in trouble. So I think this let's say these large generative AI models are really good, but maybe we have to understand how to get this huge database and to train it. So we have maybe to translate them to another area. But I'm more than happy for ideas. We really were thinking since months, everybody in our field is thinking about how can we use that and how can we further develop that. So for design, it works with that gain and with the generating that we can design. But I haven't shown it was only an auto decoder, but the next step would be, okay, can I translate the geometry in function and then only put function in, and then the geometry is designed automatically. So that's issues what we are thinking about.
Mm-hmm. Thank you. The next question. How these machine learning models in supervised learning are implemented in controllers on PLC, for example, mostly old traditional controllers?
We have one project within a milling process where we try to do it and compare it with traditional PLCs, but at the moment we only, let's say, benchmark it. What I know how you can do it, I mean, you train it and then put exactly this, let's say, knowledge in, and after, it's a black box, you can put it in. I don't exactly know what is the question when there is how it's implemented. If you are happy with the black box, then you easily can do it. At the moment, I often see it as standby or a second line and then compare it to the existing one.
Mm-hmm. Yeah, let's move on. The next question is, wonderful presentation, Professor Lanza. I would like to know if the system can work with real-time data feeds and enhance their learning, particularly for models using reinforcement learning. The real-time data can help them learn better. Will be interesting to know more about it.
Yeah, I mean, that is our huge aim, to have real data and then learning consistently. At the moment, we have to deal with, let's say, simulation models and then run it parallel. But having real data and then to learn, and at the moment we have more, let's say, a step-to-step, training in a secure environment, and then put it in the real world.
Okay, so last question from the online audience. I was impressed by the searching for patterns in point clouds. So do you assume that you have to prepare patterns for each product to compare their quality and stability?
Yes, exactly. So to be sure that you're on the right side, you need this, again, this training data, and we then try to label data to as I have shown, to then explain and to be sure, okay, the quality is high, we trust that. So it's a really huge effort at the moment to train that, yes, still.
Yeah, thank you very much. We are 10 minutes beyond the scheduled time, but let me take the privilege just to go for another question or is a comment. You know, recently Microsoft announced the Copilot. This function has been built into Microsoft 365 or Microsoft Office. This is based on GPT-4. And it can generate a different document, presentation, analyze the data in spreadsheet. Perhaps this in the future can be used to extract implicit knowledge from the CAD model as well, if properly trained. If a data are well prepared, pattern can be recognized. So that's just my comments. This will come, but we need a professional use of this powerful AI chat box.
Wow.
So before, yeah, if you have last comments on this GPT-4, please.
No, wow, I really think there is a big use, and we are still on the way to that. So maybe we even don't know the puzzle pieces or the big potential. I really believe in the big potential. And but we don't know all use case now. We are only in the beginning, searching the first maybe low-hanging fruits, and there will be a huge advantage in the future. So looking forward.
Thank you. So before wrapping up today's webinar, I want to thank Professor Lanza again for delivering this wonderful talk. And also wanted to thank all the online participants for your participation and contribute to the discussion. The next AI for Manufacturing webinar is scheduled on March 24, this Friday, at 4 p.m. Central European Time. Mr. Miller Nayaran of Tata Consultancy Services will present a keynote on AI and digital twin use cases driving sustainable manufacturing. Please stay tuned. Have a great day, and bye for now.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
you.